Thank you. Lovely words. I smile because I was recently given this illustrious introduction during a debate against a far more junior colleague who absolutely eviscerated me, so much so that it was funny, yeah. So we all can get cut down from our lofty heights. Victor and I think, have been teaching this in this computational session for 20 years nearly. And like Victor, it's always nice to go back to basics, because I think the temptation these days is to go to very complex numerical models and skip past some of the underlying basic mathematics, and that's what I'll be doing today. So I'll talk about dynamics from the ground up, and Victor already covered a lot of both of these, and then these dynamical primitives, and then I'll give a case study of the application of this theory to the human algorithm. Okay, so I usually start with this slide talking about how we go from complex neural tissue, and John introduced this, to mathematical models of individual modes or nodes. And these look like dx to t is some function of x plus I. Victor showed these as well. So x is a state vector. These are the underlying states of the system. Could be firing rates, membrane potentials. Dx to t is this change of x in time. So it's a dynamical system from the get-go. F is all the physiology that you pack into this model with some parameter A, and then, as I've shown in these with the green streamlines, some inputs from other areas or external inputs. There's the control parameter. So it's F, as Vic discussed, that's an algebraic form. There's a geometric form. F has a magnitude in this x and y space, so it gives it a vector. We have vectors all over this manifold or this phase space, and then we can draw tangents which define orbits, and these lead to attractors. And often then I skip forward to much more complex things, and today, actually like a recurrence of Vic, I'm going right back to some of the basics. So here's, I did a bit of this on the whiteboard at home because we couldn't have a whiteboard here. Here's our dynamical system. X is a manifold. We were just discussing manifolds. This is going to be a one-dimensional manifold. A manifold in this area is just any object that locally looks like your good old-fashioned Euclidean manifold. So a line, a surface, a volume, and Vic discussed these. And then we have a vector defined by F on this. And I'm starting with the simplest possible dynamical system. X dot is lambda of x. And I'm going to look at lambda less than 0. Just as Vic did, we must have been somehow internationally in telepathic communication. I put on the y-axis x dot, and on the, x-axis is x, y-axis is x dot. And that is just a straight line. It crosses 0 at 0, which says x dot is 0 there. That's a null point. Vic spoke about null clines and null planes. And so if you're there, the dynamic is invariant. You don't go anywhere. So you're stuck in that set. That's our first definition, an invariant set of the flow. Now, in this particular example, the vectors are in the opposite direction to x, because lambda is less than 0. So if x is positive, the flow is negative. If it's negative, the flow is positive. And just as Vic said, all vectors lead to the fixed point. So now we have an attractor. It's an invariant set that attracts some finite number of other points. There's various definitions. And the basin of the attraction is all those points that go to A. And in this case, it's the entire number plane. We can solve this. It's x of t is the initial condition, e to the lambda t. Remember, lambda is negative. So this is an exponential relaxation to the fixed point. We can make lambda less and less negative, and we see the flows get slower and slower, and the exponential relaxation slows down. But it's always e to the lambda t. It's always non-oscillatory in one dimension. Now lambda crosses 0 and becomes positive. the vector fields flip around and the solutions run away. So now we have our second definition, or third, which is a repeller. A repeller is a point in phase space that if you get a tiny perturbation, off goes the flow. And this transition from an attractor to a repeller is a bifurcation. I think it's the saddle node bifurcation that Victor discussed. Now we're going to just make the dynamics a little bit easier, more complex. We're making a cubic term here. It looks very similar to begin with. Lambda is less than 0, but and in fact, as you can imagine, near the origin, x cubed is much smaller than x, and we've got the same flow. And this is a very general result in dynamic systems theories, that near attractors, the Hartman-Grobman theory, I think it is, says that the dynamics become linear. But as we increase the term of the cubic term, I think I should have made a parameter there, we get this flip. Instead of it just going to be going from bottom left to top right everywhere, you see this folding, so that we've got two attractors on either side of the origin and a repeller in the middle. And the system's still approximately linear near these attractors. So now the system relaxes towards either one of these two attractors, and I'm just going to not consider x to be negative for the moment. And so we've got this distinct types of attractors, and now we have this pitchfork bifurcation, where if we increase lambda, we go from the fixed point, and just this simple cubic term creating these humps on either side, we get this plus or minus lambda. So that's the pitchfork bifurcation. Now I add a fifth order term. Playing around with polynomials is quite fun. I mean, we all did it in high school, but there are some theorems. I think it's the Chebyshev theorem that says polynomials are pretty good approximators for very complex functions, and I'm going to come back to that. These are toy models. They're called normal form, but they're good approximators of much more complex models. So with the fifth order term, I'm only showing x is positive, so it would be symmetrical on the other side, but now we've got this additional hump from the fifth order term. Now in this particular part of the parameter space, we've still got the attractor at the origin. But now as the parameter goes up, on the right-hand side, that hump goes above the x-axis. And so now, if we're to the left of the repeller, you can see the green curve is less than 0, so the attraction is to the origin. Then we've got an attraction to the large attractor and a repeller in the middle. And this is a canonical example of multistability. So we can start... I've done it all low-tech style here, just to demonstrate you can do this without any computer. That's our repeller, that's our origin, that's plus or minus, I guess it's lambda to the 1/5 or something. So now we've got two basins, and we've got what we call a basin boundary in the middle with the blue arrow. If we increase further, this repeller disappears, and we get back to the other type of flow. So here's a bifurcation diagram. On the left, on the right, it looks like we had before, but in the middle, this folds across, and we've got this period, this region of bistability. That should really be dotted. Origin and these other two attractors. So this is a regime of bistability, which is a form of multistability. Oh, there's just one other point I want to make. Often you'll see, Vic and I have shown x and x dot and these polynomials. Often you'll see potential wells like this. And so here we've got a single potential well, and here we've got one at the large attractor, and here we've got two. These are nice ways of thinking intuitively about these stable and multi-stable systems. And you can actually go from the original dynamical system to a formal differential operator on these little volume elements, and that's called the Lie derivative. And Lie derivatives are nice because they tell you how volumes contract. And this contraction of volumes onto attractors is a pretty universal property of all dynamical systems. So here's our volume elements starting big and going small, and that's why these potential well are equivalent descriptions to the dynamics, but for many purposes a little bit easier to understand. Okay, that's one dimension. Like Vic, didactically we're walking through the dimensions. Now we're going to look at two dimensions. I said a moment ago you could only get exponential relaxation in 1D, more or less. What about oscillations? So you need two dimensions. So here's Newton's law, Newtown's law. Newtown is a suburb I used to live in, not Newton. F equals ma, that's the second derivative of x. So we're going to write that as mv dot, where v is the derivative of x, and v dot is now f on m. So that's two-dimensional first-order differential equations, which are easier to deal with if you want to do the geometry. And now we have these vectors in our two-dimensional manifold spanned by x and v. So what does it look like? Let's have a look at a simple harmonic oscillator. This is like a spring whose force pulls the spring back towards the origin, and if you just pull that down, it'll just oscillate. But now we're going to, that's called the restoring force. We can talk about forces because we've got terms on the derivative. Now we're going to have a damping or friction term according to the velocity. So this is a damped harmonic oscillator. And if the damping C is very strong, the vector field will contract pretty boringly to the origin, and this is called an overdamped. If we make the damping weaker, we get this spiral inset to the attractor. This is underdamped. And now, beautifully, we've got an oscillation. So you need two dimensions to get oscillations because you can't wriggle around back and forth in one dimension. And now we can put a driving term, we can put energy into the system. So we've added this different Q, and when we do that, if the Q is strong enough, then the origin will become unstable, and now we get a little attractor going around and around. That's called a limit cycle. And if we increase Q, the limit cycle gets bigger. So we've got an unstable spiral point at the origin and a limit cycle as our attractor. So this is the bifurcation diagram of the damped driven harmonic oscillator, and it can also be super or subcritical, as we'll get to in a moment, depending on Q. A little bit fancier, but it's the same thing. This is a very simple oscillator called a Van der Waals system. So you can see as you go left and right with this Q here, or mu, you're getting onset and offset of this limit cycle. So this looks a little bit more mathematically like this, but underlying all of that, you can just get out a couple of whiteboard pens and do it on the whiteboard. A standard neural mass model, I think it appeared somewhere in John's History of Dynamical Systems, probably in the 1970s, is this rate model, the Wilson-Cohen model. And it's got a parameter J, which is the input to both sets of E or I. And so now we're going to wiggle this up and down, and you can see exactly the same underlying dynamics. So the onset, and as Victor also said, offset of a limit cycle attractor. Just to show it again, we're going left and right on this bifurcation diagram. I don't know what happened to the little pointer there. And we're going up and off a limit cycle attractor. 20 minutes, I think. Oh, there it is. So just smoothly tuning. What's really important here is that this vector field always changes smoothly because it's a very simple dynamical system. So the arrows are always very smoothly changing. And the bifurcation, the sudden change in dynamics, is because of the global topology, which is what Victor was speaking about. Not because of a sudden change in the vector field. Okay, so now we've got a little, what would we call it? A little vocabulary of fixed points. We've got nodes, saddles and repellers, spiral repellers and limit cycle. These are some of the attractors in 2 dimensions. Now we can start to put them onto into a manifold and see how they connect together. So this imaginary dynamical system's got a node, a saddle and a repeller. Now this is another important concept. Orbits that go from one fixed point to another or one invariant set to another are called heteroclines. Hetero just means different, 2 or 3. So we've got a heterocline, and I'm going to come back to that in a moment. And we can put the rest of the vector field here, and you can see we've got a fixed point on the left, we've got a repeller in the middle, which becomes a base and boundary, and we've got a limit cycle on the right. This is almost exactly the same as the dynamical landscape that Victor had, pretty much identical. But we've given talks together like this, so I guess we're in harmony. This is the base and boundary. So that's that dynamical landscape. Node, saddle, repeller. We're not going to move the fixed points. We're just going to change their stability into saddle, saddle, saddle. No attractors. There doesn't need to be attractors. In most systems, except for very poorly behaved ones, there are invariant sets. But why do we need attractors? These have got insets and outsets, and in this case, it's just a morass of heteroclinic orbits. And if we put orbits in here, you can see that they kind of get stuck and they flow in this landscape and they never really settle down. So they sort of would dwell near the saddle and then they go a little bit more quickly. Oops, going in the wrong direction here. So they kind of dwell near a saddle, faster away, and then back to a saddle. And this is formally called metastability. Now, I labour this point because in the literature you'll read meta and multistability used interchangeably, but they actually refer to very different dynamical scenarios. So metastability on the right, multistability on the left. What about 3-dimensional dynamics? We had our limit cycle in 2 dimensions, but adding a this should be third dimension, gives extra space for more complex attractors. So now we can go up and down in the Z direction and we can turn these limit cycles on and off. And this is a form of bursting. And the attractors don't have to go back on themselves, and when they don't, they're called chaotic attractors. So this is a completely deterministic system, but these orbits will never go back and recur exactly where they were before. And mathematically speaking, no matter how, if you very, very precisely give me your initial conditions, I can give you a time at which you won't be able to predict the state. So it's unpredictable deterministic flow. This is chaos. It was a great big thing. You don't see it around a lot, but I still find it very interesting. So there's the Breakspear Terry Friston. John had it in his taxonomy, made me feel very proud, if somewhat embarrassed, because it's a very archaic system. It's a 3-dimensional system. It can do bursting with an attractor like this, and with a tuning of one of the parameters, it can also do a form of chaotic oscillations like this. Interestingly, Victor spoke about potassium, and potassium plays a key role in this particular as one of the slower timescales in this system. In fact, it's the mixing of fast and slow timescales in an irrational manner. If they're rational integers, you get quasi-periodic flow. If they're irrational, you get chaos. Let's just have a look at this attractor. It's just got a fixed point. These don't disappear. And around this fixed point is a spiral repeller. But what's interesting is the orbits go up, and then they come back, and then they go back down. So there's an inset here and an outset there. And a cline that goes away and back to itself is called a homocline. And this is a homoclinic tangle. And as Victor mentioned, this was discovered in the mind of Henri Poincaré in about, I think, 1905 or so, 120 years ago, without any mathematics. So I think those of us passionate about dynamics always like to go back to this. So these are the dynamical primitives. Now we can have a bifurcation diagram, but we don't just get a hop bifurcation, we get second hops onto the quasi-periodic flow, and then we get mixing and we get this chaotic dynamics. So we get bifurcation diagrams. And if you're interested in the structure of this, you can come and have a coffee with me, because it's really extraordinary number theory going on in there. Now we're going to add noise. We had flows, and we're going to add the noise term. Stochastic dynamical system, random differential equation, Langevin equation, all used interchangeably. Victor showed this. The noise, when the attraction is weak, lambda close to 0, allows the system to explore the region of the fixed point. And actually, if lambda is very close to 0, this more or less makes a completely Brownian excursion of the phase space. In the setting of multistability, it allows the system to jump from one attractor to the other. And in the setting of metastability, it allows the system to wander aimlessly through the entire phase space, dwelling briefly near the saddle points before going off. And this is just a nicer picture of this in a review paper I wrote with Andrew, Leonardo and Luca a few years ago. The key thing here is the phase space is different and the behaviour of the system is different. At the top we've got 1 on F, scale-free excursions. In the middle we've got multi-stable dwelling near the various attractors. And on the bottom with metastability we've got a gamma function. So if you look at the fingerprints of your dynamical system and you do it carefully, you should be able to tease apart the underlying flow. I've got 10 minutes? No problem. I can slow down again. Now, I'm going to talk about a project I did with Petra Ritter and a very bright postdoc, Frank Freyer, nearly 20 years ago, and it's still one of my proudest projects, and I'll just speak about it in the last few minutes. So we have eyes closed. This is a colleague of ours, resting state EEG. You know, resting state fMRI became this huge thing in the field, but before that there was resting state EEG for decades. It was called quantitative EEG, and everybody thought it was boring as anything. But resting state EEG, now we know, and I think Johanna will show, is not boring. It's really, really interesting. So this is just resting state EEG. If you look at this was from Petra's data. We had some in Sydney. You get, if I square the amplitude, I've got power. And if we look over long periods of time, 6 minutes, you see the power fluctuates from low to very high. This is just all of you, and some of people in the room might already be eyes closed with resting state. But if we all go back to our hotel rooms and we close our eyes, this is almost inevitable. About 15 of 16 subjects that we looked at had this. So if you just do something very similar, very simple, you take the power and you do a histogram and you bin it. But this is log of the power, and this is log of the count. It's very simple. It's a histogram in log-log coordinates. And you can see this is not a Gaussian, this is a double Gaussian. This is a bimodal distribution. That's where the red and black colours came from. And then you can say, how long is the system where these two lines cross? How long is it here versus how long is it there? Black means dwelling on the left, right means dwelling on the right. And this is a dwell time distribution. And if it was a simple Poisson process jumping back and forth, linear, logarithmic, this would be this exponential PDF. But what we saw in this work is it got stretched. What that means, it's a Weibull distribution. The simple interpretation is the longer the system dwells in one attractor, the less likely it is to jump to the other attractor. Engineers know this as a time-dependent failure rate, and I'll come back to it in a minute. So that was from the data, and we published that in Journal of Neuroscience, and then Frank came and stayed with me, and we're like, well, if it's bimodal fluctuations, let's find a bistable dynamical system. So we started with this fifth-order polynomial. I've spoken to this before, but that's the amplitude R, and we're going to give theta an angular rotation, and this gives it the 10 Hertz oscillation. So we cheat a bit, but that's another type of the normal form of the Hopf bifurcation. And if you vary theta and beta, doing it properly this time, as I began, you get supercritical and then subcritical bifurcations. 2 parameters. And now we can go, okay, I said, Frank, put noise into the system. And off he did. We've got sub, super, and intra-metastable. And it looks pretty good, right? You've got no oscillations, high amplitude oscillations, and multistable fluctuations. Very similar to what Victor was showing at the end there. But then when we did the plotting of the power, something really weird jumped out. Because this is a logarithmic axis, if you're just adding the noise, you don't get the scaling. In linear coordinates you would, but in logarithmic coordinates, as you go up, if the width is the same, then it gets narrower and narrower. So we thought about this and decided that it was the wrong sort of noise. We couldn't have simple additive noise. That's what I showed before. I called it the Langevin equation. Now we're going to put in a second term. This is another noise term, but it's multiplied by the state. What's it doing? As the amplitude gets bigger, the effective noise gets greater in amplitude. So we've got, now you need this boring term, the linear term, because as the amplitude goes to 0, that will turn off and you'll get stuck at the fixed point. So that's just keeping the system alive, and that's making the fluctuations bigger and bigger. And as you can see on the right, when we did that, you get up the top scale invariant fluctuations in your power fluctuations of the alpha rhythm. So that's the normal form. On the left, we've got a human, and on the right, we've got this very simple fifth-order polynomial with this multiplicative noise term. And because this is a model, you can go right across the parameter space, and for any individual, you can pull out the parameters. So we've got EEG model, EEG model. So you can actually fit these 4 parameters to individuals. It's all very well behaved. So we published that in a PLOS-CB paper, and then we went to this neural field model. Victor showed aspects of it. James, you might be talking about the neural field model. This is something I worked on as a junior postdoc with Peter Robinson. If you put noise into this model, you'll get EEG data looking alpha fluctuations. You can also get seizure onset through Hopf bifurcations, and this is exactly what Victor was showing. In fact, I'll just show it again in a moment. What we're doing though is we're turning the noise term off. That Laplacian, delta squared, is a second order time derivative, a space derivative. It gives the waves, but we're going to turn that off. And lo and behold, we've got our damped driven harmonic oscillator. So this complicated neural field theory that hardly anybody understands unless you've stared at it long enough, like me, is just a damped harmonic oscillator with a spatial term thrown on. Peter Robinson, by the way, hates it when I describe it like that. It's true, it's not really, but it'll do. So there's our damped harmonic oscillator. This has got a 3 Hertz bifurcation, not bifurcation. I swear this is autocorrect doing this. And that gives us a petit mal or absence seizure. The 10 Hertz subcritical gives us this highly asymmetric grand mal-like seizure. Victor spoke, he's got a whole taxonomy of these things. And so Frank and I and Petra decided to try and find a smaller amplitude Hopf bifurcation in the neural field model. And we used a tool in MATLAB called DDE BIF tool. We could plot out the whole family of bifurcations in this much more complex model from supercritical through to subcritical, pick the subcritical, and put noise into the neural field model and reproduce these lovely bistable fluctuations with Weibull distributions and scale invariant noise. So these are two universal properties of human cognition. First of all, Weber's law. There's a whole lot of laws that are scale-free, perceptual performance, where if we're sensitive to 2 Hertz at 20 Hertz visual flicker, we're sensitive to 4 Hertz at 40 Hertz flicker. And movement, if we move slowly, if we double our speed of movement, we double our errors. Everything in the brain is scale invariant. So how did we get this into the model? And this will be my last slide. In the neural field model is the thalamus, and it is a relay center to and from, as you can see in the cartoon here, the cortex. And this is the term. Normally there's just a noise term. And now we've got this noise multiplied by phi e, which is the cortical term. And this is the term here. So we've gone from a complicated a simple normal form model to a complicated neurophysically derived neural field model, but underlying all of this is the same sort of mathematics. So there's a person and there's the model. And yeah, this is one of my favourite projects that I've worked on. And it's an example of multistability. When Vic was speaking and showing some of the more recent work, I really wanted to put up some examples of metastability in brain waves, but there's no time for that. Vic presented the virtual brain. You can learn all about this in a MATLAB-based toolbox. I know MATLAB's not very popular or cool or fancy at the moment, but this is a beautiful way of getting into simple dynamical systems. It comes preloaded with a whole lot of models. We were starting to do this in Python. Now I'm finding out that Python isn't cool, so we're going to do one of these Jupyter notebooks. But this is what the Brain Dynamics toolbox looks like. Oh, okay, I went past my acknowledgement slide. But thank you very much, and to all my collaborators and students.
Thank you so much, Michael, for this. I'm sure you've inspired the audience. I was wondering if there's 1 or 2 questions before we move on to the next session. Does anyone want to make a comment? Yes.
All right, hello. Thank you for the good talk. So I'm just wondering that when you modeling the human EEG data, so then the state vector becomes just the EEG signal from the only sensor, or you use some kind of source inversion method before that?
We use the world's simplest source method, ICA, just unmixed signals. You don't even need to do that. You can just look at channels. You'll see all these dynamics in an occipital channel. If you do an ICA and you get an unmixed linear mode, these bistable fluctuations really jump out of the data very strongly. I mean, we could and will take, and Victor's done this, a neural field model and put in a lead field observation model, add some noise. But, I mean, it's nice when the dynamics jump out so strongly that you don't really need this. But you're going to follow up with something?
Actually, this is my first time to see this thing. So, all right. So this is so inspiring. And actually, I thought that this method thing seems like very dependent to the dimensionality of the vector, it seems like. So how many IC component did you use for that?
Look, it's a really stable thing.
Oh, really?
You can do, I think we had 64 channels. We probably did 64 ICA, threw out some noise. What's interesting is that if you look at the mu rhythm, you'll see another ICA component, and it's also doing bistable switching. A lot of the brain rhythms do. At higher frequency, and we just published this recently with a Finnish group, you'll see criticality as well, avalanche dynamics. But most of the low rhythms, theta, alpha, mu, you see these strongly bistable switches. Thank you.
All right, thank you very much.
We should get on to the next speaker, I think.